Welcome back. In this video, we are going to start with chapter 4 about connected topological spaces. There will be 3 sections in this chapter, and I will split the first section into 2 parts in order not to make lengthy videos. Okay, now fortunately, the notion of connectedness is easier to understand than the notion of compactness. Okay, it's more intuitive. So, intuitively, a space is connected if it's topologically one piece, so cannot split it into more than one part. Okay. But of course, we have to make this more precise. What do we mean by splitting or separation? So let us start with the notion of separation. So if you have a topological space X, a separation of X is a pair, UV, of 2 subsets of X, which satisfy 4 properties. 4. They are both non-empty. They are disjoint. They are both open, and they cover X. The union is X. Okay? So it's a special kind of partition of X. And we say that X is connected if it does not possess a separation. Now, 2 remarks before we give examples as usual. If UV is a separation of X, then U and V are complements to each other. So, therefore, if U is open, then V is closed. And since V is closed, is open, then U is closed as well. So both U and V are closed and open at the same time. We say that they are clopen. Okay. This does not happen in any topological space. Okay. And other remark is that, as we said, a separation of a space is a partition of that space. But not every partition is a separation, because we can always write any set X as the union of a subset of X and its complement. So we have 2. So A and its complement are disjoint, they cover X. And if A is not empty, okay, then X, so if A is a proper subset of X, then also X minus A is a proper subset of X. So not empty, not the whole space. But the point is, in the definition, is that both A and its complement must be open. Okay? So don't confuse partition and separation. Separation is a special kind of partition in 2 sets. Now, let us give some examples as usual. First example, if you consider the set capital X of all points in R, whose absolute value is strictly bigger than 1. But this is a subspace of R. This space is not connected. Why? Because we can write X as the union of the interval -infinity -1 open and the interval 1 plus infinity open. Okay, and these 2 open intervals are, of course, open in R and therefore open in X, and they are disjoint and non-empty. So we have a separation of this space. So this space is not connected. Clearly, it consists of 2 pieces, 2 intervals. R star also is not connected, because R star, which means R without the origin, can be written as -infinity 0 open, union 0 plus infinity open. And these 2 sets are non-empty, open in R, and therefore open in R star, disjoint, and so on. Now, note that -infinity 0 open, this interval, is open in R and therefore open in R star, but it's also actually closed in R star. Why? Because its complement is open in R star. Okay, so this may be a confusing point. So please go back to the section on subspaces, topological subspaces too. So this is to -infinity 0 is not closed in R, but it's closed in R star. And we shall prove later that all the intervals of R are connected. Okay, so actually, and we shall prove that the only connected subsets of R are the intervals. And this should be intuitively clear, because an interval, including R itself, is one piece. Okay. But proving this rigorously by going back to the definition is not totally trivial. But if you understand this, then it's fine. It's a good start. Now, of course, a trivial example of a connected space is the empty set, because you cannot split the empty set into two non-empty sets. A singleton is also a trivial example of a connected set, because you cannot split a singleton or a one-point set into two non-empty subsets. The only non-empty connected subsets of the rational numbers are the singletons or one-point sets. Yeah. So, of course, we know that the empty set and the singletons are connected, so we have just to prove the converse. So we have to prove that if a subset Y of Q has more than one point, it cannot be connected. So it has a separation. So consider a subset Y of Q and that contains more than one point, A and B. We know from a fundamental property of R that between two rational numbers, I can find an irrational number. So there is an irrational number C between A and B. Now I can write Y as the union of these two intervals, Y intersected with the open interval minus infinity C, and Y intersected with the open interval C plus infinity. Now these two are not empty. The first one is not empty. For example, if A is less than B, C is between A and B, so A is here and B is here. So these two sets are not empty. They are clearly disjoint, and the union is Y. Okay, because C is not in Y because C is irrational. Okay? So I have a separation of Y, and therefore Y is not connected. Last example. If we have a set and we consider the collection containing just two elements, the empty set and the whole space. Now, I didn't mention this explicitly, but it should be clear intuitively that this collection containing just two sets is a topology according to our definition of a topology, okay? Because it contains the empty set and the whole space. Any union of these two elements is either empty or X, and any intersection is either empty or X. So it's a topology that we call the indiscrete topology, and this is the smallest topology that we can put on a set. Okay? It's not interesting, but X equipped with this trivial topology is of course connected, and this is also a trivial case. Why it's connected? Because I cannot find the only open sets in this topology are just two, empty set and X, so there are very few open sets, so cannot really separate cannot split X into two disjoint non-empty sets. Okay, so this concludes the first examples that you need to understand. Now we move to the first result. If we have a topological space X, then the following conditions are equivalent. First condition, X is not connected. Now we know what does this mean precisely. X, so it has a separation. Second condition, there exist two disjoint non-empty closed subsets of X whose union is X, and we already observed that, so not a novelty. Third condition, there exists a proper Klopen subset of X. Klopen means both open and closed. Proper means it's not empty and it's not the whole space. Okay. You already observed that. Last condition, there exists a non-constant continuous function f from X into the set of integers Z. So let us do a circular proof. 1 implies 2, we already observed that. If you have a separation AB, now this you can note the separation by AB, CD, UV, anything you like. So if you have a separation AB of X, then as we observed, A is closed because B is open, and B is closed because A is open. So we have now a partition into two closed sets instead of open sets. 2 implies 3. Also, it's trivial because A is not empty and it's not the whole space, so it's proper and both closed and open. So observe that. 3 implies 4, little bit less trivial. So we have to prove that there exists a non-constant continuous function f from X to Z. So by 3, we know that there exists a proper Klopen subset, A, capital A of X. And now we take simply f to be the characteristic function of A. Also, the characteristic function of the complement of A would do as well. Okay, so this function just takes two values, 1 and 0, 1 on A and 0 on the complement of A. Okay, now this function is continuous. Why? This is a simple exercise in set theory. How do I know that a function is continuous? I look at the inverse image under F of open subsets of Z. And if we take O to be an open subset of, or just any set, actually, the inverse image under this characteristic function takes just, there are four cases. Either it's empty if O does not contain 0 or 1. It is A if O contains 1 and not 0. It's the complement of A if it contains 0 but not 1. And it's all of X if O contains both 1 and 0. So prove that, actually. It's a good exercise. So therefore, it's continuous according to our definition, and clearly it's not constant because it takes two values. Okay. So in the fourth case is actually the empty set A, the complement of A and X are of course open. All right. So the inverse image of an open set of Z is an open set of X. Yeah. So this concludes 3 implies 4. Now 4 implies 1. Okay. So suppose that we have a continuous function f from x to z that takes at least two values, a and b, two distinct values, a and b. We know that any singleton z is open. Okay, and we explained why in chapter 1. Because, for example, you can write a, the singleton a, as the open interval a minus 1, a plus 1 intersected with that. And since f is continuous, the inverse image of this singleton, so instead of writing f minus 1 of the singleton a, we write simply f minus 1 of a. Okay. So since the singleton a is open and f is continuous, then the inverse image of this singleton under f is open in X, and of course not empty. And on the other hand, the complement of a is also open because the singleton a is closed. And therefore, its inverse image under F is open. And therefore, now we have a separation of X. We can write X as the union of the inverse image under F of A, which is an open set, and the inverse image of its complement. And these two sets are disjoint, non-empty, and open. So we have a separation of the space. So X is not connected. Okay, and as a corollary, just negate everything. So a space is connected if and only if there do not exist two disjoint non-empty closed subset of X whose union is X. If and only if the only clopen subsets of X are the whole space and the empty set. If and only if for every continuous function f from the space to z, every continuous function from the space x to z is necessarily constant. Okay, so just negation of. Okay, so this is an elementary fact. Now, remark, what we are in practice, we have to deal with topological subspace of a given space. So we have to understand when this subspace is connected according to our definition. If you have a topological space and the subset y of x, y, as you know, inherits a topology from x called the subspace topology, okay, that we explained in chapter 1. So we say that y is connected if it's connected as a topological subspace on its own, which inherits the topology from x. Okay, and so, but sometimes it's easier to deal with open subsets of the bigger space x. So we have this characterization. Y is not connected if and only if there exist two non-empty subsets A and B whose union is Y, and such that these two conditions holds. B does not mean the closure of A, and A does not mean the closure of B. Now here, don't be confused, because A bar, so of course, if A union B is Y, then necessarily A is contained in Y and B is contained in Y. So A and B are both subsets of Y. But A bar denotes the closure of A not in Y, but in the bigger space X. Okay. Now in the proof, this will become more clear. Okay. So we have to prove two implications. Suppose first that Y is not connected according to our definition of separation. So there exist two disjoint non-empty subsets A and B of Y that are clopen in Y and whose union is Y. Okay. Now, in an exercise of chapter 1, we proved that the closure of A in Y is simply the intersection of Y and the closure of A in the bigger space X. Okay, so saying that A is closed in Y means that A is equal to its closure in Y. So it means that A is equal to A bar intersected with Y, where A bar is the closure of Y of A in the bigger space X. Okay, so now A bar intersected with B. Since B is contained in Y, B intersected with Y is just B. So I can replace B by B intersected with Y. And so I get A bar intersected with B intersected with Y, or A bar intersected with Y intersected with B. But A bar intersected with Y is just A, so this is just A intersected with B. And since AB is a separation, the intersection is empty. Therefore, A bar intersected with B is empty. And a similar argument shows the symmetric condition, okay, because A and B play the same role here. So this is one implication. If Y is not connected according to our initial definition, then there exists a separation in this more general sense. So of course, AB is a separation. Note that the A and B are closed in Y. So their closure in Y are disjoint. Okay, but we have something here. But the intersection of the closures of A and B need not be empty, as we shall see now. Okay, now conversely, suppose that we have a separation of Y in this new sense. So Y is the union of two non-empty sets A and B that satisfy this disjointness condition, which is actually stronger than A intersected with B is empty, but in this case they are equivalent. So now we claim that A bar intersected with Y is just A, where A bar, as we said, is the closure of A in the bigger space X. And it will follow then that A is closed in Y. And similarly for B. So why this is so? How do we prove this equality? Double inclusion. Of course, A, as we noticed, is contained in Y, because Y is A union B. And of course, A is contained in A bar, so A is contained in the intersection. And conversely, we take an element small x in the intersection, and we prove that it's in A. So we reason by contradiction. If X is not in A, then necessarily, and since X is in Y, then necessarily X is in B, because Y is A union B. Okay. But then X would belong to A bar and to B, but the intersection is empty, and this is a contradiction. Therefore, X is necessarily in A. So any element here is here, and therefore we have equality, and the same argument works for B. So it follows from this claim that A and B are closed in Y. So AB is a separation of Y according to the initial definition, and therefore Y is not connected. So this can be useful in practice because it's easier to work with open or closed subsets of a bigger space. Now, let me give an example that illustrates this slight differences between the closure of a set in Y and the closure in the bigger space. If you consider Y, take Y to be Q and X to be R, then we can write, and so we just take capital A to be the set of rational numbers which are less than radical 2 strictly, or the set of rational numbers X whose square is less than 2. And we take B, the set of rational numbers whose square is bigger than 2. So this is now, of course, a separation of Q because A is open in Q and B is open in Q, and they are disjoint, and the union is Q, of course, because radical 2 is not in Q. So we have now a separation of Q. Now, A bar, the closure of A in R, is, as we proved in the exercise of chapter 1, is, as you expect, the closed interval minus infinity radical 2. And the closure of B in R is the closed interval radical 2 plus infinity. But of course, once again, the closure of A in Q is simply A, actually, because A is closed in Q because B is open in Q. Okay, so we have here, so A bar intersected with B is empty, and A intersected with B bar is empty. However, the intersection of A bar and B bar is radical 2, and this is not empty. So Now we'll end this video with a lemma that we'll use later. If we have a topological space X which is not connected, so it has a separation CD, and we know that we consider a connected subspace Y of X, because the whole space need not be connected, but it may contain connected subsets, as you may expect. So if X is not connected and has a separation CD, and we know that Y as a subset of X which is connected, then either Y is contained in C or Y is contained in D, and not both, of course, because C and D are disjoint. Okay, this is not difficult. So since we have a separation, CD is a separation, so CD are both open, not empty. And by definition of the subspace topology, C intersected with Y is open in Y, and D intersected with Y is open in Y. And these two sets are disjoint, and they cover Y. If they were both non-empty, then they would constitute a separation of Y. But Y is connected. So therefore, one of them is necessarily empty. So either C intersected with Y is empty, and in this case, Y is contained in D, or D intersected with Y is empty, and therefore Y is contained in C, and that's it. Okay, so this concludes this useful lemma that we shall use later. So now I will stop this video at this point and continue in the next video. Thank you for your attention, and see you next time.